All right, so let me readjust my window because I realized it's a little smaller. Okay, so like I mentioned before, is that this is mostly going to be kind of review for you guys because we did this in version 1's module 1 curriculum. I think statistical distributions in particular, we talked about, I want to say section 9. So I think section 8 and 9 is really what these past sections 17 and 18 have been kind of covered. There are some new stuff, so just know as you go through it, if you guys haven't gone through it already, you'll see half of it's new, half of it's stuff you've already done before. So I'll kind of go briefly to there, but just know that you can reference the other stuff we learned. So this is going to be the same notebook we've seen. So this is when we first introduced statistical distributions. We talked about randomness going through. I'm not going to go into that whole thing, basically making sure, you know, we have that seed, right? And that's how we can get randomness. So then we can build like an actual statistical distribution. And this is what we had right here. In this case, we had a normal distribution. And I'm just going to kind of run this stuff so that way we can kind of see it a little bit. But when we run a, oh, there we go, forgot to run that guy. Okay, so in a normal distribution, we can basically, also called the Gaussian, we can basically define it with the average, which is usually defined as mu. It usually looks like, let's see if I can do this right on here. Nope. But if you were to, let's see here, I'm trying to show you guys, so when you guys see it in like a paper, for example, you guys would know it's, I believe that's what give us it. No? Oh, I'm getting the wrong backslash. There we go. So that's, for example, mu, right? That's usually noted as a population average. And that's basically you need mu, your average, and you would need the standard deviation, which is usually represented and not by mu, but instead by lowercase sigma, which I think you guys have all seen this point right here. And with those two parts, basically, you can create any random distribution. In this case, you can see here, NumPy actually uses this normal distribution. We can create a we can create random data from a normal distribution. And so we already know what kind of normal distribution looks like. In this case, it's not quite, you know, perfect, but if you, this is actually from this data, I'm sorry. But if I were to put in this part, sorry, I realized I overwrote this, so let's do that. So I can show you the normal distribution. There's our normal, okay. Beautiful bell curve, right? So bell curve, normal distribution, Gaussian, they more or less mean the same thing. Sometimes there's implications of what they're scaled down to, but essentially they're all the same. And you can see here in the red is our average. And then we can see here on the left and the right is basically one standard deviation away. And that defines our whole basically bell curve. And so basically if we do something random based on the normal distribution, we would basically get most things will be towards the center, towards the average. And then as we get further and further away from that average on the standard deviation on the tails, it's less likely. Okay, so review stuff, right? Normal distribution sound good? Thumbs up if you recall this, looking good. Cool. And if there's something like, you're like, wait, I don't remember this, or like, can you just repeat this part? Definitely stop me. Okay. So I'm going to go through this really quickly because we already done this. Probability mass function. Basically, it's more a discrete part. And so basically, it's kind of like if you imagine these are bar charts, essentially what we have going on here. So that's our PMF. I just realized I'm just going to run this all. That way I don't have to run individually. Okay. I think that ran it all. Cool, okay. All right, so statistical, our PMF right here, and you can see this is a stem leaf plot, for example. So this is a PMF or probability mass function. And then we'll talk more about actually doing something like a CDF, like a cumulative distribution function, right? And so a CDF basically is another way to represent the same information. And basically it's accumulated over time. So basically all CDF plots stop at the top at 1.0, okay? And each point is basically saying how much more. So as you kind of, for a bell curve, for a normal distribution, you will see a structure that looks kind of like this. So go down right here, and then I'll kind of speak up like this, and that'll be closer to a normal curve. I mean, that's a little off, but like basically if you have a huge spike in the middle, that's what this is representing. So you can imagine a huge spike and going down, that would be the actual normal distribution, like our PDF, which we'll see in a second. But that's just one way to show it. And this can be useful because then we can kind of see how it accumulates together and see that change. All right. Here we have our PDF, our probability density function, which is very similar to the probability mass function, but density means basically, so we have a continuous variable. So you can hear like these bar charts can be represented essentially like as a PMF, and then this blue curve right here would be the equivalent PDF. And this curve, for example, might be generated. We're going to skip over this, but just know that the reason we have to be careful about basically making sure we have a range that we're talking about with the probability. You can't say a specific point because basically a specific point is a probability of 0. So always keep that in mind. So you can see here we have an area underneath the curve basically going from 12 to 14. Okay, and here you can see all three basically put together. We have our CDF, which is in the blue here. You can see that nice curve. And then we have our PDF in the black here. So this is probably a parameterized, basically using the bell curve structure. And then we also have, in this case, it's just normal. This is from a graph I had taken from another website. But this normal, basically, you can think of that as being our PMF, basically our little bar charts where each individual point is. Okay, cool. Any questions on PDF, PMF, or CDF? Yeah, go ahead, Giovanna. Oh, yeah.
I was mute. I just want to know what is a CDF good for? Like, what will we use it for?
Yeah, it's in a lot of ways, it's the same information, if that makes sense. Like there's nothing new out of it. It's just another way to compare our distributions. So if you had multiple distributions, you might, for example, compare the CDF on, let's say, I think of it like a natural language processing. So let's say you have two different books and say what words are the most common and stuff like this. And you might, for example, see a CDF of seeing how frequently those words are used. And you would have it basically add up to saying what's the most common. And your CDF might look differently depending on what book you're looking at or specific data. So another one, maybe a little more familiar with us, would be something like home prices, and saying like our home price might be, we'll just pretend it's normally distributed, is that you have some home prices that are very, very low and then some home prices that are very, very high, right? So you'd have this kind of bell-like structure, and you can represent that with a CDF right here. But if you wanted to compare one town to another town, maybe some towns have more skewness, maybe they're a little, or not skewness, kurtosis, like more of a peak, maybe they're skewed over. You can, it can be kind of cumbersome to put the bell curve on top of each other, and a CDF might be more useful in that way, just to visualize it. So in a lot of ways, like I said, like the data is the same, or data are the same, like being represented. It's just more like another way for you to visualize it. So at this early stage, it probably makes sense for you to try out different ways of visualizing it, because as you see more and more ways, you'll start seeing when things are more useful for you to basically, like the visualization really, it doesn't really tell us any actual, like I like to say, it doesn't tell us any actual information. It's not giving us a numerical quantitative thing, but it allows us to very quickly see a general shape and get an idea of what the data is like, or data are like. Okay. Does that answer your question, Giovanna? Cool. All right, any other questions? Cool. All right, that was very nice. All right, and so visualizing a PDF, so I kind of mentioned there's a parameterized one, which is basically using a normal curve. Essentially, we use the equation for a Gaussian, and we basically say, all right, it's going to be a Gaussian, and you basically figure out what the standard deviation is and what the average is. A more non-parametric would be basically taking each data point and using like a kernel density function, or KDF. Usually you'll see this, like they use a KDF. And basically what happens here is it's a much more organic shape. So the reason why we do this is basically we're able to mathematically model each point as Gaussians, like little tiny Gaussians, and add up their contribution together to make an overall fit that's easier, mathematically easier to kind of form versus just like us drawing a line, if that makes sense. And so, for example, if you ever do like wave dynamics in physics, this is like literally the same exact thing. Hopefully, I know that sounds like very intimidating if you don't know physics, but basically it just means that you can make any function you want by just adding up these different distributions together. So yeah, hopefully that kind of makes sense. Any questions on this? This is probably very, yeah, I see a little scrunch up face and maybe not. Basically, you can kind of think like we pretend each point So I'm going to go why this works is that we pretend each point we actually measured it is at that specific point. And if you did the real thing, the thing that you're most likely to measure is the average, right? That this tends to be the most common thing you'll measure, but sometimes you'll measure it off to the side. So basically what it measures is like, well, this point could have been off a little bit to the left, or this point could have been to a little bit to the right. And basically we do that for every single point. It's like, well, this point could have been off to the left, could have been off to the right. And so we essentially we're repeating this experiment over and over again and pretending like we're mathematically pretending that we're doing this experiment over and over again. And we would get for each data point that would have been in the center here, spread out in this curve. And we basically add up all those contributions and say, okay, what if we took 1, 2, 3, 4, 5, 6 different points, and we said we did some little bit of randomness to it. And basically if we did a little bit of randomness to it and you did this experiment over and over and over and over again, this would be the shape of it. So hopefully that kind of makes a little more sense. If you had all the points like perfectly measured at like this center right here, you would have a nice bell curve underneath, because basically you can assume like each point, that's where the truth is in a way. But sometimes we might measure it a little bit off to the left, a little off to the right, and that would create a bell curve. So that's kind of my quick hand wavy of why this works. I don't know. If you have more questions, definitely we can go more in detail if you guys would like. Yeah. Sound good? Thumbs up? Thumbs down, being like, no, Victor, I don't know what the heck you're talking about. Okay. I'm gonna assume you guys just being nice, but okay, we'll take it. And so you can see here a comparison for a parametric fit, which would be like the bell curve. You see that in that green right here. You can see the actual data itself in here. And you can see the kernel density estimation. I'm sorry, I said KDF earlier, it should be KDE. Usually you see KDE. And that kernel density basically estimates what the real data looks like. And you can see it fits a little bit better because we can see it's not exactly bell, it's kind of got this flat top. And this is why KDE is really useful, but we sacrifice the that accuracy with the beauty of mathematics. Usually these calculations are a lot easier to find. For example, finding exactly what the average is here is a little trickier, like compared to like here. Like the average, like, well, technically the average is right here, but you know, it's not as pretty. If we model as a bell curve, we say that's exactly where the average is. So we sacrifice accuracy essentially for, you know, ease of mathematical use. So that's kind of like what we're doing here. Okay. All right, so that's a KDE versus our parametric normal distribution. Like I said, a bell curve. Here's our equation, right, for a Gaussian, also bell curve. You can see here, it looks very complicated, but basically it's just, these are some numbers. The square root of 2 pi is a number. E is just a number. And then X is our actual, what we measure. And mu is our average that we have. And our sigma is our standard deviation that we already discovered. So it's pretty much, what's it called? It's basically all you need to know for a Gaussian to build it is essentially what's the standard deviation and what's the mean. And with that, we can do this nice, cool 68, 95, 99 rule. And there's more general rules, but basically we know how much data should fit in there if the data actually follows a bell curve. So we always try to strive for this. And as mentioned before, like way before, we have a z-score. Basically our z-score is saying how many standard deviations are the, what's it called? How many standard deviations are the, or is the point away from the average? So that's essentially what's going on here. And the reason why we use that is basically it's a nice thing. So like if the standard deviation is like 1 versus 100, depending on different distributions, we can just say, well, okay, like the standard deviation for the housing price might be like a standard deviation of 10,000, right? But the standard deviation for like, I don't know, number of like, I don't know, baskets made in a game by a basketball player might be in the orders of like tens. Like, well, in order to compare those things, we can basically just create a z-score, which we say, okay, it's so many standard deviations away. Okay, and that's why we can do this stuff. Right? And we'll see this in our t-distribution. Okay, and then we talked before deviations from the normal distribution, skewness, right? Here's positive skew, negative skew. So this is skewed off to the right. This is skewed off to the left. So you get the idea, right? And I think this is actually something that's people sometimes mess up, is the skewness is not the bulge. The skewness is the thing that's pulling it off to the side. So you can see here is that it's skewed off to the right here. So you can see it's a positive skewness. Basically, it wants to be this nice normal, but something's kind of pulling it off to the side where these things are a little more likely than you normally would expect. And same thing on the opposite here, it's skewed off to the left. It's kind of being pulled off to the left over here. Okay, cool. And kurtosis is basically how specky it is. Right. Statistical tests. So this one I kind of not skipped over, but I kind of went through this very quickly. We'll see this again when we actually do A/B testing and other hypothesis testing. But I kind of mentioned it right now. Is that statistical significance? Basically, we want to see how many from our z-score, how using the z-score, it's like, okay, we're like 2.3 standard deviations from the mean. How likely is that? How likely would that happen? And using that, basically, well, how likely it is essentially is using our p-value we've mentioned before. So we can basically decide on how far, or not how far, but just like, is it statistically significant that we were this far? Like, is it more likely, how do I say it? Is it just by chance, like, oh, we just happened by accident, you know, just measure this very particular value? Or is it like, oh, this is so unlikely that there's probably something else going on? That's really what a statistical test is, hypothesis test is saying, is that we're saying, well, the null hypothesis, right? Oops, I don't know, I just all messed up like that. There we go. The null hypothesis, usually H0, is saying that nothing happened. It's like, it's just pure chance. Like the reason why you measure this is probably just probability. It's probably probability, right? It's just randomness. The alternative hypothesis is like, no, there's actually something going on here. It's not just random chance. Something did actually occur here. There's some weird thing. So for example, if you're measuring between taking a placebo versus taking some medical drug, and you find that it's really, really unlikely that the drug, by pure chance, just that people happen to be better with the drug than the placebo, then you're like, well, okay, the drug probably is actually working. That's the way we kind of phrase all of this stuff, okay? And we measure that how likely with our p-value. And again, I'll point down to this article and video of p-value with puppies, which is an amazing little video. Basically saying how likely is it if you found your dog like this, is it that your dog got into the trash can, or is it more likely that, you know, or is it someone tried to come in the house and frame the dog? It's like, well, that's unlikely. So that's kind of like what the p-value is really measuring in a lot of ways. So it's a good article, and also there's a nice video if you don't like to read as much. I think it's linked here somewhere in this article. Okay, cool. I did it again. Sorry. And I'm resizing all these windows. Okay. So that's my quick going through XKCD. Just be careful with p-value, measuring things over and over again. I won't go into full example. And of course, there's the one sample z-test. We'll see this again with our t-tests, but there's also a great walkthrough by one of the other instructors, Jeff. Okay. Any questions I kind of quickly went through? I know the only reason I'm doing this is because it's relative review. Okay. Sound good if I move on then? All right, I see nods.